Oh yeah, you could drop into the net and then apply to the edge. Well, yeah.
I'm sorry, you're PhD students, not postdocs.
I'm a postdoc. Oh, you are a postdoc. Excellent. Okay.
Thank you.
I'd like to get my PhD in postdoc.
There, like, yeah.
Okay.
I still put doctor on my slides because it wasn't that long ago and I'm very excited.
Yeah, you should just keep putting doctor on your slides.
Like, absolutely.
Okay.
I started a webinar and I think it auto started recording, right? And
I think so. Yes.
Or
yes.
Looks like, yeah.
Yeah, it should have just started recording when you clicked that. So.
Yeah.
There. Yeah. All right. Okay. Shall I go ahead and get us started? Hey everyone, thank you so much for coming to our Popping the Science Bubble lecture tonight. I'm going to lead us with a land acknowledgement, and then I'll introduce the group and the program, and then you'll get to hear from our science bubble organizer and the scientists themselves. So, Berkeley Public Library buildings are built on the territory of the Puchun within the homeland of the Chochenyo-speaking Ohlone people. We acknowledge and honor the Ohlone people who have lived in Berkeley and throughout the East Bay since time immemorial. The library recognizes that Berkeley residents have and continue to benefit from the use and occupation of unseceded stolen land. And we pledge to recognize the permanence and the rich contributions that the Ohlone people continue to bring to the city of Berkeley and throughout the East Bay. We celebrate the strengths of the Ohlone people and their culture. The Berkeley Public Library is committed to helping create a more just and anti-racist society, and to furthering the visibility and celebration of Ohlone authors who are specific to the East Bay and Ohlone culture in our collections and programming. This is a living document that was co-written by Ohlone cultural leaders Vincent Medina and Louis Trevino and the Berkeley Public Library. Thank you. All right, so welcome to Popping the Science Bubble. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic they find really interesting. The organizers are 2 graduate students at UC Berkeley, Kaylin Swan and Daniel Bretthauer. This program happens every 3rd Tuesday of the month at 5:30 p.m. at the library and on Zoom. If you're interested in checking out their past seminars, you can visit their website and sign up for the listserv to keep in the loop for upcoming seminars. Also, check out their YouTube page. It has a lot of past lectures that are great, and Macy's lecture will be uploaded there. So, thank you.
Cool. Thank you, Kelsey, for the introduction, and welcome everyone. Thank you for coming to this month's Popping the Science Bubble seminar. My name is Kaylin, and like Kelsey said, we have seminars every 3rd Tuesday of the month, and at the end of the talk, we'll also have a QR code where you can scan and get on our listserv, as well as browse all of the past YouTube videos that we have on archive for the last couple of years. So it's a great resource, and please check it out. And so now I am going to introduce the first speaker of the night, Dr. Macy Huston. Macy grew up in Ohio and got their undergraduate degree in engineering at Ohio State and PhD in astronomy and astrophysics at Penn State. Macy worked on a variety of research topics related to the formation and evolution of stars and planets in the Milky Way. They're currently a postdoctoral researcher in the Moving Universe Lab at UC Berkeley and continuing work on gravitational microlensing. In their free time, Macy likes to hang out with their wife and cat and crochet. So take it away, please.
Thank you. I won't do my own little intro then. I'll just get started.
But today I'm going to talk about my research about black holes and how we find them through the light that they bend. Okay, already having a problem. There we go. So I'll just start by talking a little bit about what black holes are. I'm sure you've all heard of black holes, but just to talk about a couple of the technical details of them. A black hole, it kind of has two key locations that describe what it is. So there's a singularity. This is a single point in space. It's not like an extended object that has a volume, but it's just a tiny point in space that contains a bunch of mass. This theoretically shouldn't be possible under like classical mechanics as Newton understood it, but we know through relativity, as Einstein described it, that this is actually possible. And so in a black hole, we've got that central point called a singularity. Then the other important location is this radius that surrounds it. That's called the event horizon. So the event horizon is just the distance away from the singularity where light can no longer escape the gravity. So the image quality didn't blow up very well, but here we've got a visualization of a person with a flashlight under the event horizon, and all that light just gets bent around heading back towards the singularity. Whereas a person outside of the event horizon can shine a flashlight and send that light all throughout the galaxy, but it's just going to get bent a little bit by the black hole, but can still fly off to other destinations. So as a quick little look at how black holes form, this is just kind of a chart describing the basics of stellar evolution. After stars are born, they will kind of exist for a long time, like normal, like our sun is right now. And then eventually they go through some kind of dramatic process where they might explode, they might shed some layers, they might implode, and these form kind of the end products of stellar evolution. And so for low mass stars, including our sun, these will generally turn into white dwarfs. These are pretty compact objects. They're a lot smaller than normal stars, but they are still luminous, and we still are able to see them for a while after formation until they cool so much that they're not giving off much energy. The next size up of stars, more mass, a few times the size of our sun, form neutron stars. So these are even more compact objects. Its mass is going to be a little bit greater than the mass of the sun, but its size is actually about the size of a city on Earth. So these are incredibly dense objects. And then when you have even higher mass stars, like 10 times the mass of the sun or higher, roughly, that is going to end up as a black hole, where we get a singularity of that single point of infinite density. So that's
Can you just describe what the middle section is? Is that the
that's the red giant phase. So stars have their normal main sequence lifetimes where they're operating like the sun, and then as they run out of hydrogen to burn, then their cores will sort of collapse while the outer layers expand, and that's when they turn into red giants.
Let's say what a very large mass star is.
Yeah, generally about like 10 times the mass of the sun. Yeah, and higher than that too.
And do we have an example? Is there some example, like a named? Something we'd recognize. We go past Star Wars, the way to the grocery store.
You know, I'm not sure I have one off the top of my head.
Okay,
actually. Beatrice is a red giant. I don't remember what its original mass was actually. It could have been a really high mass one. I'm not sure.
It is large enough to go black hole eventually.
Okay.
Which one was that?
Beetlejuice.
Oh, okay.
Yeah, Beetlejuice is a red giant. Yeah. Okay. So now on to the more complicated picture of stellar evolution. It's not actually as simple as the last picture I showed. There's actually a lot of different ways that stellar evolution process can happen. So as we can see in our example here, we kind of have a couple examples of a star like the sun and a star that's a little less massive. And these both turn into white dwarfs, but only the higher mass of that category actually involves a supernova. The other ones just kind of collapse in a much less dramatic sense. And then when you move up a little bit in mass, we can get neutron stars. And again, we can kind of have a couple different processes happen. And especially with like the red giant phase, stars can kind of dramatically undergo changes in density. And you know, some of the interior mass of the star come up on the outer part and even reignite hydrogen fusion. So that process can happen in different ways. And then with the higher mass stars, we also see black holes can either form through a supernova, they may form from direct collapse. So they may go straight from that red giant phase just into collapsing straight into a black hole, and there's no supernova to see. And then we also think that for especially high mass stars, we might even get supernovae that just explode all of the material away, leaving nothing behind to turn into a compact object. No neutron star or black hole, just a bunch of gas flying out into space. So there's actually a lot of open questions in science about how exactly this works. A couple of the big things are we don't know the kind of mass cutoffs that we talk about for whether things form a white dwarf, a neutron star, or a black hole are not absolute lines. It's dependent on the mass, but also things like the composition of the star, so how much of other elements is in there beyond hydrogen and helium, as well as whether there's any other stars nearby that could be gravitationally interfering with what's going on in the star as well. So there are still a lot of open questions in the formation of black holes. And so this is something that we are working to study.
What's a blue supernova?
Yeah, so that's a phase it kind of goes along with the red giant process, but for larger stars that are hotter. For hotter stars, the light is more blue. For less hot stars, it's more red.
And when you say some of them just collapse, then they're just gone.
Well, they would just be a black hole then.
But weren't there some that don't become black holes? The biggest one,
yeah.
Well, that's the supernova. But I was wondering about the small.
Yeah, the direct collapse we think only happens for really high mass stars that will turn into black holes. We don't really think that happens exactly in that way for other masses of stars.
Can you say in a sort of general ballpark way what the time frame is for these kinds of processes?
Yeah, so the main sequence life of the star, if it's a star like the mass of the sun, it's going to be about 10 billion years. The main sequence is the longest phase of a star's life, other than the end product, I guess, which could be there forever. But the main sequence lifetime is while it's still fusing hydrogen in its core. And so actually higher mass stars are like hotter and more compact in the center, so they burn through their hydrogen more quickly. So that time will go down to hundreds of millions of years, even tens of millions of years for like high mass stars. And then yeah, those other more dramatic processes that we see at the end are going to happen more on like the thousands, 10 to 100,000 of years. Things go pretty quickly near the end. But these are all very long processes, so we can't watch this process just happen to a single star, unfortunately. So we have to just look at stars during all of these different phases and kind of piece it together with those snapshots. So the snapshot of that I work at right now is looking for black holes. Let's get that. I had some extra stuff if we have time, but we have a lot to talk about. So
We have lots of time too.
Oh, so okay. You're good. Well, I was also just going to mention supermassive black holes real quick because I'm sure you've all heard about it a little bit. Especially it was in the news a couple of years ago when the Event Horizon Telescope was able to take the first images of supermassive black holes. So these black holes are a lot different than the ones I studied. They are millions to billions of times the mass of the sun, and they lie at the center of most of the galaxies we know about, including our own. This is an image of our own supermassive black hole. So I just wanted to kind of give a shout out to the other end of the mass spectrum of black hole research. That is really exciting too. So,
is it okay to ask this questions?
I'm fine with it.
So it lies at the center of most galaxies. So it's really the center. It's like the focal point of a galaxy is.
Yep. Yeah. Basically, it's right at the center, and then all the stars are kind of just.
Are they going into the black hole?
Sometimes they are, especially when they're right at the center and there could be like friction processes that pull them in. Other stars might not necessarily have a reason that their orbits would change, but yeah. Okay. So black holes do not produce their own light. As we mentioned, light cannot get beyond the event horizon. So we have to be a little creative in the ways that we study them. And we look at their effects on other objects. So one of the ways that we do this is by studying accretion. So accretion is what happens when there's kind of some matter surrounding a black hole. This could be the remnants of a supernova process, or it could be some gas coming off of another star nearby it. And so this gas will start to spiral into the black hole, and it'll create a disk of material that's creating friction and heat, and it'll radiate in a way that we can actually observe. So this is one of the ways that we can spot black holes. Another one is through companion stars. So this could go along with accretion, where you have a companion star that, if it's in its red giant phase, it's got some outer layers that are really puffed out, and those can start to drift off of that red giant star and start accreting onto the black hole. And you might also just see that a star's motion on the sky or through its radial velocity indicates that it's moving on an orbit. And if you can measure the mass of that system, then you can determine that there is a black hole at the center of it. And that's one route that some other members of my group work on. Another really interesting field in astronomy that's really grown in the past decade is gravitational waves. So this will happen when you have a couple of really compact objects like black holes and neutron stars that are orbiting each other, and those orbits will decay and they'll kind of radiate gravitational waves. We can't quite detect that gravitational wave background of these objects just in orbit yet, although there are instruments being built to do that. But what we really can see is when those objects actually merge, this really dramatic collision event where they just form one black hole. They'll emit a bunch of gravitational waves at that time, and we've got some instruments like LIGO that can detect that and figure out what the mass of that final object is. So this can be a way that black holes kind of build up and increase their mass over time. To me, the most exciting way to study black holes is gravitational microlensing. So this is what happens when a black hole happens to pass in front of some other distant star in the background in the galaxy. So this method's kind of unique because it doesn't require another star or material that has to be interacting with the black hole. It's gonna just be moving through the galaxy, and there's just other stars doing their own thing in other parts of the galaxy, and they happen to cross along our line of sight as we look out into space. And so we'll get into some detail about how that actually works, because there's kind of a lot going on here. There's a top-down artist illustration of our galaxy. So we are out here on Earth, and we are observing this star off in the background, far away. And then we have a black hole here. It can be any massive object, but we'll say a black hole here that passes in front of that background star on our line of sight. And it'll bend the star's light around it, focusing it towards us here on Earth.
And then you know it's a black hole.
We don't necessarily know right away, because anything with mass can do that. It can be planets or other stars. So we have some other steps that we need to figure out whether it really is a black hole. First, we'll take a look at this from another angle. So this is actually what you would see looking out from Earth if you have amazing perfect resolution, which we don't have, and I'll get to. But this is the black hole here. And we have a luminous star passing behind it. And as that happens, the lens, the black hole acting as a lens, is going to focus its light around this ring around it that we call the Einstein ring. And so we're going to get these really weird two warped images of the source star, the background star, that are going to move around the Einstein ring, and then it'll go back to normal when it gets far away from the black hole. And so there are kind of two different signatures that this can produce that we can measure, and we can combine these things to figure out whether it is a black hole or some other type of lens. So there's the brightness and the position of the star that we can measure. So these are kind of complicated, so we'll go through each kind of angle of it at a time. The first is photometric microlensing. So this is really similar to the animation we were just looking at, where we have the lens object here, stationary. It's Einstein ring around it. The red empty circle is the source star, the bright object that passes behind it. And then we saw those weird warped images before. Those are shown here now just in blue instead. But with our current technology, for the vast majority of microlensing events, these images are way too small to actually get an image of. And what we can see instead is it just looks like there's one star there, but that star will look like it changes a little bit. And so what we actually see is that the star, as its area appears larger while it gets warped, we can kind of add those areas together and the star is going to appear to be brighter. So this is just showing over time, what does the brightness of the star appear to be? And so you'll get this spike when it's closest to lens, and it'll go back to normal as it moves away.
And we're looking at, and we're like,
Yep.
Okay.
Yep. Is that clear enough?
That one is just what it looks like if y'all are infinite view.
Yeah, if you're zoomed enough to see the images separate. Yep.
Would it always be symmetric?
No, not necessarily. Especially if there's a planet orbiting the lens star, there's a way that we can detect planets. You'll get little perturbations on the light curve. You'll get some other little bump where the brightness just goes up a little bit for a few hours, typically for a planet.
Can you give some intuition as to why the shapes look like that with the two different stretched out? Why does it go like that one way down the other way?
Why does it split like that?
Yeah. So yeah, with the lens object, the light gets bent around the Einstein ring. So what the Einstein ring really is if the lens and the source were absolutely perfectly aligned, it would be lighting up a perfect ring following the Einstein ring. But generally, that chance, the absolute perfect alignment just doesn't really happen. So there's usually a little bit of space. You can see here the source star doesn't actually go right behind the lens, but it's close. And so when it's a little off from the center, that means the images will go to the side of the Einstein ring.
Give intuition as to why the Einstein ring works. Why does
General relativity, it's described by a bunch of equations. That's just, based on the distance between the objects and the mass of the lens. Those are kind of the factors that go into it. So the more massive the lens is, the wider that ring is going to be. And the stronger the effect we'll see on the light is.
But there might be some explanation like the black hole tends to pull the light towards it, but not quite making it all the way because of the
No, yeah, that is, yeah. The black hole is pulling the light towards itself, but it's not pulling it, all the way in to its center. It's just kind of bending it because mass will kind of warp the shape of space. So just the path that the light follows just kind of changes a little. Yeah. Okay. The other side of this is even more complicated, but this is the side I'm really focused on right now, so I wanted to talk about it. This animation is kind of similar to the last one we looked at, but here we're keeping the source stationary on the sky, so we can view it in a particular way.
The source being the black hole.
The source is the bright object.
The bright object.
Yes.
Okay.
Yes. The black hole is what we call the lens.
Okay.
Yeah. So the source is stationary here as the open circle, and the lens passes in front of it. You can see those same blue images. Those just look the same as we were seeing on the previous slide, but we have the addition of this red dot. And so this red dot is basically the average of those two blue warped images that you see. And so the red dot and its position is really what we basically see with our telescopes today. And so you can see that it follows kind of a weird little curved shaped path on the sky during the microlensing event. And so this down here just kind of puts that on a larger scale, where you can see that the star that we're looking at is just going to appear to move around a weird little circle as that event happens. And this usually happens over the course of a couple of years for a black hole lens. The events will be shorter if you're looking at smaller objects like planets or lower mass stars.
Shorter meaning weeks?
Yeah, the typical microlensing event lasts like a month for stars. So this motion is incredibly small on the sky. It's just a very tiny wiggle that a star will have. How strong that wiggle is dependent on the mass of the lens. So we have better chances with a high mass object like a black hole than we do with a planet of actually being able to detect this. And there's only really a few telescopes today that are capable of detecting a signal like this. It's requires really, really good resolution.
Say the timeline was the order of, say, weeks or months?
For a black hole, it would be more like a couple years.
So you're using a telescope that can see them.
Yes.
Where is it?
Yeah, so there are a few that you can use. Actually, I'll talk about them in a second.
Oh, okay.
So, yeah. Great. I'll move on to the first example then. So we have detected a black hole this way one time so far. This is a very new field. It's a very new technological capability that we can even resolve this. And this is a discovery that was made by the group I'm in here at Berkeley, but before I joined it. So this is a project led by Casey Lamb, who was a grad student in the group at the time. She's now a postdoc at Carnegie Observatories. And Jessica Liu, who is the professor who leads our group. And so this was a really exciting discovery because this was the first discovery of an isolated black hole. Every other black hole that has been discovered in the past has been observed through its accretion or companion star or gravitational waves. This was the first one we had found that was just by itself. It didn't have anything in its orbit that was able to give it away. And so this is an image of that bright source star that they monitored. It's called OVO 2011 BLG 0462. I won't say that too many times. But if you're interested in the naming scheme of astronomical objects, it's the name of the survey that found it, the year it was found, the region of sky near the galactic center, and the number of the microlensing event in terms of how many they had detected so far that year. And so in this example here, we can look at how the brightness of the star changes over time. You can actually see the star is really bright in the first image while it's being lensed. Then it gets dimmer and dimmer as it goes back to normal. And so this is...
When you detect these, it's not a human being looking through the telescope. It's a computer.
Yeah. Yeah, there'll be a telescope that goes onto like an electronic detector that'll like count the number of electrons. Then that'll go into a computer. Yep.
What's moving to make the changes? Is it the black hole? Or
yeah, it's the black hole passing in front of it. And the black hole and the star behind it are probably both moving a little bit, but they're both moving very slowly. So you can't like detect it by looking at these by eye. You might be able to numerically on a computer.
And so the final one is with the whatever the object was that was going into the lens is back to what is normal.
Yeah, this is the star back to normal when it's no longer within the Einstein range. Okay. So it's no longer bright.
And then it just stays in that.
Yep. It'll just stay
then you know you're done.
Yeah. Yep.
So what does it feel like from August 8th to October 31st, and that's quite a bit smaller? And you go to August 31st on the 9th in the next year. It's considerably smaller. But why is it such a big gap from September 2012 to August 29th, 2017? 5-year gap.
Yeah, there was some data taken in between these. I think this was a choice for this picture just to show what it looks like when it's back to normal. There was some data taken in between, which didn't show all of them because it'd be a lot. So this is a little bit more of the technical kind of figure that we look at to see how the position of the star kind of diverges from a linear path. Most stars are just moving in a straight line across the sky, but we can detect these weird little dips and bumps and figure out that that is a microlensing signal. So with this, they were able to confirm that the lens is a black hole and that it's about 6 times the sun's mass. So am I short on time? Probably. Okay. Okay. Then I'll talk a bit about what we're doing now to try to find the second one. So we've got a number of different projects going on. The one that I'm very focused on right now is, the previous one I think I may have mentioned was discovered with the Hubble Space Telescope. Unfortunately, the Hubble Space Telescope had some technical problems come up lately, and it's now much more limited on where in the sky it can point. So it's not really the best telescope to use for this anymore. So now we have just recently started using the James Webb Space Telescope, which is a newer telescope that is in the infrared light, and it launched a couple years ago on Christmas. I got up early and watched it. And so, yeah, we're using this telescope to monitor one new microlensing event right now that is our black hole candidate. We just got our first data in September, so that's really exciting. But we only have one astrometric point. We don't have a curve yet, so we can't tell yet whether it's a black hole. But we're continuing to watch it, and I am submitting a huge proposal tomorrow to try to get more time for that. So, busy time for astronomers this week. It's a big deadline.
Who do you get your money from? To continue. Is that what you're talking about?
Well, this is to get time on the telescope to take those pictures.
Okay.
Yeah. And when you're proposing like that for a NASA project, that does come with some funding to analyze the data then afterwards.
So is there a waiting list of people that want data from the telescopes?
There's one time a year, there's a deadline that you submit your proposals for, and they get like 10 times more proposals than they have time for the year. So it's like very competitive. Yeah, it's very competitive. And so, yeah, the best way to do this project is from space, where you don't have the atmosphere interfering and decreasing your spatial resolution. As light comes from the stars through the atmosphere, that's going to decrease the quality of your image. The light's going to get distorted by the air and the currents in the atmosphere. So we really like to do this from space, but there's only a couple space telescopes and it's hard to get time on them. So if we want to kind of try to find some more of these, we got to work from the ground too. So one of the ways that we do this is using the Keck telescopes in Hawaii. And these telescopes are able to actually measure what's going on in the atmosphere, and they have a deformable mirror that their light goes through, that they're able to, in real time, deform the mirror in order to compensate for what's happening in the atmosphere and get the light back into its normal shape as it would be coming in from space. So this, those systems aren't perfect. It's not quite as good as getting images from space, but it's pretty good. So we're also working on studying some microlensing events in that way. I've actually got one that I'm working on right now where we have detected an astrometric microlensing signal. It actually doesn't look like it's a black hole though. It's not quite massive enough. We think it might be a neutron star, but we've got a little bit of work left to do to confirm that. And then lastly, there's another space mission that's coming up that's really exciting for this project. So the Roman Space Telescope, which is going to launch in May 2027, is going to be able to simultaneously measure photometry and astrometry. It's got a field of view that's about 100 times Hubble's. So you're actually going to be able to capture a lot of these events just by chance without specifically choosing and targeting them.
But person, how big, so the Roman one is 100 times the Hubble one. How much is it?
It's in between their sizes, but closer to HST. So yeah, the Roman telescope mission was actually, well, this portion of it was designed for detecting exoplanets. So in addition to finding black holes, it's also going to find over 1,000 exoplanets. And we're going to be able to learn a lot about that from exoplanets that we can't find with other techniques. So planets that are a little further away from their star on like an Earth-type orbit or a little larger than that. So that's very exciting as well. Yeah. Roman? The Roman Space Telescope. Oh, that's somebody's last name. It was named after Nancy Grace Roman, who was an important NASA member. Nancy Grace Roman. I should have spelled it out. Pardon?
So how do people typically find possible candidates of black holes? Like, if you have so many images and there's probably noise, and do you have an idea of where one could be, or?
Yeah, so
could you kind of repeat the question?
Yeah, so kind of how we find candidates for black holes to study in this way.
Where do you focus?
Yes, so there are a bunch of active microlensing surveys that are able to monitor photometry. They're from the ground. They don't have high enough resolution to measure astrometry themselves, but they're measuring photometry the whole part of the year that we can view the area near the galactic center. They focus on regions of sky where there's a lot of stars, so you're more likely to get these chance crossings, because you can't really predict microlensing events. You just have to watch a bunch of stars and wait for them to happen. And so we look at these photometric surveys who issue alerts when they see an event starting. Then we look at those events and see There's a couple different factors we count on to figure out which ones are good black hole candidates. This would mean they're long-lasting events, which can indicate that the object is a high mass. There's also another factor which we call microlensing parallax. So this is related to as Earth orbits the sun, we're viewing these stars at a slightly different angle throughout the year. And this can actually kind of distort the way the light curve looks. It can distort how that photometric signal looks over time. So we can also select based on that to look for objects that have a high mass as well. So yeah, we select from photometric surveys and then do astrometric follow-up on the very best candidates we can find.
So if you're detecting these events, and because there's relative motion between the source and the black hole, I'm wondering how often there's relative motion between the stars. In other words, if you look out and take a picture and see where all the stars are, and a couple weeks later, take another picture, high resolution. Are they all kind of shifting relative to each other, or to what extent are they?
They are, but it's so small you wouldn't see it visually.
But over time, you would see it. Because if you can detect that change with the black hole and other stars are moving, that's a common happening, that stars are moving relative to each other. And maybe the map would always be changing.
Yes, yeah, it is. It's generally hard to see, but it will happen. And this is actually another part of what we do in microlensing is like 10 or 20 years after a microlensing event, you take another picture and the lens and source might be far away enough from each other that if they're both luminous, you can see them as separate objects. So that does happen over time. Yep.
So obviously there's a massive black hole, the big ones that have the galaxy. There's the stellar black holes, the ones that are from normal stars, not the galaxy. And what about primordial black holes?
Yeah, so the idea of primordial black holes, let's see, this is a long one. They come from a theory of dark matter. So dark matter means that there is some mass in our galaxy. We can tell by how stars orbit our galaxy that there's some additional mass that's causing gravity, but we can't see it visually. There's not enough stars to explain that mass. So one theory that could explain that is primordial black holes, which means there's a bunch of black holes that theoretically would have formed before our galaxy did, before all the stars in our galaxy did. And that because they were isolated black holes, there's no way to see them, and they could just be moving through our galaxy without us knowing. Microlensing surveys are able to put limits on that, and we know that you can't explain all of dark matter through primordial black holes, but it is still possible that they exist. That's something that microlensing surveys are trying to answer.
Also, another theoretical thing. What about black hole stars?
What do you mean by that?
The hypothetical stars in which they were so massive, like the beginning of the universe, towards the beginning of the universe, there was so much mass that they could actually get so large that their core would actually become a black hole. But like it wouldn't even be able to the star. Like this entire star wouldn't. It would be like a shell star, and the entire star can't get eaten because it's so large. Yeah. And so they grow really big. The star consumes a bunch of stuff. So the black hole grows, and so they just star.
That has been proposed. It's not something we have confirmed. The problem with that is that's a really hard thing to confirm because if all you're seeing is the bright exterior of the star, and you know that there's some mass inside that, there's not really an easy way to tell whether that mass is in a black hole or if it's just a star in there. So that is an interesting open question in science that's going to be really hard to answer.
It would pose a very conclusive answer to like how the massive black holes like Tom 618 are able to get that big without just like merging with each other, because that would take too long.
Yeah. Supermassive black holes are so large that they're hard to explain. We don't know exactly how they get that large.
Is the Roman Space Telescope going to find any exomoons, like the possible moon of J1407B?
Yeah, I know there are some people working on simulations right now to try to figure out how possible that is, and it is definitely possible. We don't know how common moons are, so it's hard to say whether it is common enough that we'll happen to see one, but it's definitely an exciting possibility, and we really hope to find some.
Time for one more question, if there's any. Not, Macy could perhaps stay also at the end of the talk if folks have any questions. And thank you again for a very exciting talk.
Good luck on your proposal.